4.2, properties of rational function. Alright, the technical definition of a rational function is as follows. Alright, a rational function is a function of the form r of x equals p of x over q of x, where p and q are polynomial functions and q is not the zero polynomial. I should probably also put here that the domain is all real numbers except where the denominator equals 0. Okay, so for example, if I were to find the domain of these functions, all you need to do is set the denominator equal to 0, and that is what is not included in the domain. This is what x cannot be, okay, since the denominator cannot equal 0. So the domain is from negative infinity all the way to negative 5, and from negative 5 all the way to infinity. For this one, if I set this equal to 0, you factor this. This is x plus 2, x minus 2. Hopefully you guys remember your difference of squares. So x equals positive negative 2. So the domain is negative infinity to negative 2, negative 2 to 2, and 2 to infinity. For this one, if you think about it, there is no way that this can equal 0 if you have a real number for x, because anything squared is never going to be a negative number unless you have an I. Okay, if you have a real value for x, it's never going to be a negative number. So this domain is going to be all real numbers. There's no real number I can plug in for x to get negative 1. Okay? Alright, for this one, I got no x on the bottom, so it is also the set of all real numbers. And last but not least, negative infinity to 1, and 1 to infinity. Alright, so these are the answers. You guys go ahead and try this one. Alright, example 2. Analyze this graph. Alright, if you graph it on your calculator, it looks something kind of like this, except it's a little more symmetrical and a little bit more neatly drawn. The domain, write this down, the domain is all real numbers except x equals 0. Okay, so we've got from negative infinity all the way to 0, and from 0 to infinity. Okay, there's no x-intercept and no y-intercept. Okay. If you want, you could also talk about the end behavior. You could talk about how it approaches, as x approaches infinity, f of x approaches 0. As x approaches negative infinity, f of x approaches 0. Some things like that. Here, let me write that out. Alright, this is a notation that we haven't discussed yet in class. The limit, the way you read this is, the limit as x approaches infinity of h of x equals 0. What this means is that if you look at this graph as x approaches infinity, the graph is getting closer and closer and closer to 0. Okay? So the graph, as x is approaching infinity, the graph is getting closer and closer to 0. Also, as x is getting closer to, as x is approaching negative infinity, it's also getting closer to 0. So that's what this is saying. As x approaches infinity, the graph is approaching 0. As x is approaching negative infinity, the graph is approaching 0. If this is confusing for you, ask me about it in class tomorrow, and I'll go over it again. Okay? Alright. Graph this rational function. You guys all have graphing calculators, so I'll just go ahead and graph it. Alright, so the graph looks something like this, what I want you guys to notice between this graph and the previous graph is that they're pretty much exactly the same, except that this one has shifted. It's shifted up 1 because we've added 1 outside the parentheses, and it's shifted to the right 2 because we've subtracted 2 inside the parentheses. Okay, so you actually could have graphed this without a graphing calculator because you already knew what this graph looks like. Okay, but it's okay if you use the calculator to do it. I'll let you guys go ahead and try this one. Alright, horizontal asymptotes and vertical asymptotes. You've actually already kind of seen these here and there in graphs. Alright, once again, we're going to go over this notation more in class, but if as x approaches negative infinity or as x approaches infinity, the values of f of x approach some fixed number L, then the line y equals L is a horizontal asymptote of the graph. And we've done a couple examples of that. Okay? If as x approaches some number A, the values of the function approach infinity, then A is a vertical asymptote, and this can be from the positive or negative side. Alright, this little negative here means that it approaches A from the negative side. This little positive here means it approaches A from the positive side. And we will do some examples of this in class, so don't worry. If it's really, really confusing, let me know and I can go over it some more. Alright, locating vertical asymptotes. A rational function r of x equals p of x over q of x in lowest terms will have vertical asymptote x equals r if r is a real zero of the denominator q. Alright, what the heck does that mean? Let me do an example. Whoops, scroll down a little too far. Find the vertical asymptotes of any of the graph of each rational function. So, if we were to go about looking for the domain, we would set the bottom equal to 0. And then we would factor this, we'd get x plus 2, x minus 2, x equals negative 2, x equals positive 2. Okay? These are the vertical asymptotes. Voila, you're done. Okay? Likewise, for this one, I've got x minus 1 equals 0. You add 1 to both sides. X equals 1. And that's how you do it. This one we already went over. This one cannot equal 0, so there's no vertical asymptotes. This one, if you factor it, you should get x, let me see here, x plus 7, x minus 3 equals 0. So x equals negative 7, x equals, whoops, positive 3. Is that the last one, or is there one more? Nope, that's it. Alright, so I'll let you guys try the one over here. Proper rational functions. By the way, you guys, I'm just realizing now that there might be some moments in in this video or in previous videos where my voice sounds a little bit muffled, kind of like this, the way it sounds right now. And I just realized that there have been moments when I've been accidentally moving the mic away from my mouth. Because of the software I'm using, I can't go back and redo those parts. So I think you can still hear my voice, but if you have trouble hearing certain parts, just let me know, and I can let you know what you missed in class, okay? So just make a note of anything you couldn't hear, and I can go over it in class. Alright, proper rational functions. I'm just going to write it out. Alright, proper rational functions. If a rational function is proper, the line y equals 0 is a horizontal asymptote of its graph. Alright, so finding horizontal and oblique asymptotes. Horizontal are the ones that are like this, straight across. Oblique asymptotes are also called slant asymptotes. Okay? So I'm going to list out some rules here. Alright. If the power of the numerator, in this case n, is less than the power of the denominator, in this case m, then the rational function is proper, and y equals 0 is a horizontal asymptote. Okay, so anytime this degree is less than this degree, y equals 0 is your horizontal asymptote. If they are the same, or if n is bigger than m, then one of these three things is the case. If n equals m, oops, then y equals a over b is your horizontal asymptote. If n is 1 more than m, then you have an oblique asymptote, y equals ax plus b. Okay, and you can see what a and b are from this equation. If n is 2 or more, bigger than m, then there is no horizontal or oblique asymptote. Okay? Alright, find the horizontal asymptotes, if any, of this graph. Okay, so as you can see, the degree of the top is 1, the degree of the bottom is 2. So in this case, m is bigger than n. The degree of the top is smaller than the degree of the bottom, so it is proper. So y equals 0 is the horizontal asymptote. All done. Don't know why I gave you so much space. I think I gave you space just in case you wanted to graph it out and see graphically how that is. Okay, so to find the horizontal or oblique asymptotes, in this case, where the degree of the top is 1 more than the degree of the bottom, we know from this that we're going to get some line, y equals ax plus b, but we don't know what a and b are. So, hopefully you guys remember from Algebra 2 how to do long division. So in this case I've got x cubed minus x squared plus 1 being divided into 3x to the 4th power minus x squared. So, what do you multiply x cubed by to get 3x to the 4th? Well, you multiply it by 3x. You multiply that by everything in here, you end up with 3x to the 4th minus 3x cubed. There's no x squared, so plus 3x. Okay? Then you subtract. Make sure you distribute the negative sign to everything inside the parentheses. So here I have 0. Negative and times negative makes a positive, so I've got 3x cubed minus x squared minus 3x. Okay? So now what do I multiply x cubed to get 3x cubed? Oops. Just multiply by 3. So now I've got 3x cubed minus 3x squared plus 3. I'm going to put the 3 over here so you don't accidentally subtract from the x's. Once again, make sure you distribute the negative to everything inside. This becomes 0. Negative x squared minus negative 3x squared, you get a positive 2x squared. Negative 3x minus 3. Okay? So, this is what we have. When you divide this out, you end up with 3x plus 3 plus 2x squared minus 3x plus 3 over x cubed minus x squared plus 1. Now, in this case, the degree of the bottom is bigger than the degree of the top, so this would tend to 0. And our oblique asymptote is y equals 3x plus 3. Alright, I'm going to save the last 2 examples for the next video. Alright?